Okay. So we've talked about our files and our programs, and we can sort of see how when we're writing a program on a file, it would be written in a certain way according to the syntax of the programming language, and we'd be using it for a certain thing just to handle a specific goal that that programming language can handle. And okay, we were all fine and dandy. We've written our program, just theoretically. How do we turn it into an exe? Well, we talked about we need some form of translation step. Let's look further into that with compilers, right? Code exe, right? Okay, let's talk about some ground rules. Whenever we are interpreting, or we're, sorry, not interpreting, we're handling our code, first things first, the behavior of our code is going to be the, our behavior of our code is very important. Our exe has to reflect our code, right? Or sorry, reflect. Exe has to reflect the code. So we can't randomly add, like if our program is just hello world, right? Just a simple print statement, we can't randomly add a Bitcoin miner into the code, right? Like a Bitcoin miner cannot be added to our code. We want hello world. We do not hello world plus Bitcoin miner, right? We can't add nothing like that. Whatever we write in our code, we has to be reflecting, it has to reflect in the exe that is produced. Right? That's called program correctness. Second off, the exe has to be able to run on our computer, right? We cannot create. You've heard before the header and the magic numbers and stuff, right? Remember, a Microsoft, the magic numbers of Microsoft exe are 4D5A, or M, that translates to MZ in ASCII, right? MZ is our header. That that Microsoft Windows header that won't run everywhere. We need to or we need to make the exe run wherever it needs to run. Correct? Right. Okay. All right. Let's get started with that. Okay. First thing that needs to happen: code. Our code. We need to understand the structure of our code. If we don't understand the structure of a code, we don't. We cannot have program correctness. Where does that happen? That happens in the IR. Now we're starting at the middle, right? Okay. So roughly in the middle of the running of our compiler, we will achieve program structure. We will know what the program structure is. Right? Now, once we know the program structure, we can go on to the back end of our compiler, which does some stuff and eventually spits out an exe, right? So backend spits out an exe. Then we have our input and code, and the incoming code, its purpose is to get us to that IR, right? It's called a front end and a back end, right? Okay. Front end, back end. Okay. Let's look more deeply to how do we interact with the IR, or how do we make an IR? Sorry. First thing, in order to make an IR, actually, I'll erase this for now. Okay, in order to make an IR, the thing that we do with that, the thing that we make an IR with is called an abstract syntax tree. That's very nerd stuff. From now on, we'll be calling it an AST. Basically, AST tells you the order in which you are going to be running your program. Right? So, for example, in this program, assuming we're running exactly like this, right? We don't do anything else to it. 2 times 2 is going to be the first thing that's run. We're not gonna we're not going to just give x as 2 times 2. We're going to turn that into 4. Then we're going to give it to x, right? Then we'll run the condition. If we'll check, does 1 is equal to 1? If it goes, then it'll actually will 1 will run. If not, it'll just print x as 4. If it is true, then it'll print x as 1, right? Okay. So we know the order of our code with the AST. All right. Now, we don't, uh, ASTs are not universal. There's not one way to make an AST. We have to have some rules in place in order to make some, and in order to make code that can be turned into an AST. and we use that with something called a context-free grammar, right? So in order to sort of understand it a little bit better, look at it here. We have x equals 2 times 2, right? That's a variable, and we'd have to, so whenever we're looking for a variable, we have to check for the equal sign, right? Is x equal to? So we have to check, is there some variable here? Is there an equal to sign here? Is there something here, right? We split them up. When we're checking for conditional, we look, is there a conditional? If we're looking for an if statement, we look, is there an if statement, right? And then we read off a condition. We treat this like a condition that we will interpret to see if what way our program goes, right? The two very different ways of interacting, or those two very different things that we want to do, and you cannot, whenever you're looking over it, it's like, where is it? Where is our stuff? Where is our stuff? In order to fully understand a variable assignment, which is line 1, and a condition or if statement, which is line 2, we have to, there's different elements that we need to handle differently. So we have our CFG, which is find and dandy, which tells us, okay, assuming you have all whatever elements, you can do, and this is how you make an abstract symbols tree. But on its own, the CFG would have to be very, very complicated, and it'd be very, very painful for the CFG to just go individually, have to manually go and look through all this stuff, right? But what if we told the CFG, okay, there's a list of 50 things that I can give you. I'm giving you this one thing, right? So instead of having to have it read over, have an understanding of our program structure in order to make an AST, it could just take in a bunch of take in like 50 possible instructions that you give it and turn those into an AST, right? Which is much easier for the CFG. And the thing that creates those tokens, right? So we look through our code, we say this is a variable assignment, it's x is being assigned, x is the variable, and then this is what's going to be set, or the variable is going to be set to this value. And we say var assignment of x and 2 times 2, and we give that to the CFG, and we say this is a variable assignment, these are our conditions, and that is called a token, and a lexer is the thing that makes a token, right? Okay, our lexer makes the tokens, and then the CFG and the AST both come together in the parser, right, which sort of understands the structure of our language, right? Okay, so our lexer takes in our code, it splits it up into a like list of, and just like a number of possible things that the uh, grammar, what's called the grammar is just like the thing, CFG, that G stands for grammar, so I'm just going to call it grammar from now on. Our grammar can only takes in a like set list of possible instructions, so our lexer, just for ease of use and not making it super complex, so our lexer passes or understands the code, it turns it into those tokens, and it gives it to the grammar. And what the grammar does is the grammar turns it into an AST, which once again captures the flow of our code, and then that is distilled into an intermediate representation, right? And okay, now we have the intermediate representation, we have our program structure, now we can go about doing other stuff. Okay, let's first talk about something. Look at this code real quick. What is always going to be printed out, right? 1. 1 is going to be printed out all the time because that's just how this code is looking right now. So we don't need all of this code. We only need print 1, right? That's all we need. So there's a step called optimization, which lets you trim down a code and say, I want to make my code, let's say, faster, or more memory efficient, or smaller, or whatever, right? You say, okay, I want to optimize for some task, and you go optimize it, right? And that's called, and once you have an IR, you would optimize, and let's just sort of see how a computer would handle that. First thing, it handles it in what's called basic blocks, right? So basic block is how you split up code so you can individually look at it, right? So we have uh, this first basic block this first basic block, and it's x equals 2 times 2 if 1 equals 1, and yeah, right? hmm And we have our second basic block, x equals 1, and third basic block, print x. Just from this graph, like, where do you think basic block starts and ends, right? Okay, it, it starts, or well, the thing that sort of separates our basic block is where is there an if statement, right? So our basic block, the intention of the basic block is to be straight code until it runs into an if statement. So the code should run in order, ding, 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 and there shouldn't be any, it should consistently run like that, ding, 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 every single time you run the basic block, right? So for example, in the first one, x equals 2 times 2, that will run, then the condition will be checked. Once the condition is checked, then it can go in two different directions, right? But while you're checking that condition, it'll still be in that same order. You still have to check in the condition before you can branch it, right? And yeah, and we would optimize these individually. So for example, basic block 1, we turn that into 4. We turn this in x equal to 4. We turn this x if true, right? X equals 1 is fine. And then print x. X is fine. So we individually go in this first basic block, we patch it up a bit. We say, okay, we do this optimization. X equals 1. I don't know what, or we can't do an optimization here in this basic block. And then print x, we can't do anything here. So, okay, we now have our optimized basic blocks, and we turn them, those basic blocks, we turn them into what is called a control flow graph. Basically, we would ask ourselves, okay, how does it run? How does our code run? And it first starts at basic block 1, right? It starts at basic block 1, and then there's a branch, right? Now, if it's true, right? So I'll say true. It goes to basic block 2. And if it's false, it'll go to basic block 3. And then once this is run, it will also go to basic block 3. Now, we've optimized basic block 1, and we see it's always true, right? So we don't even need this condition. We can cut off this condition, okay, and it becomes BB1, BB2, BB3, right? So we know x is equal to 4, x is equal to 4, x equal to 1, and then print. That would be our stuff, right? Now x is equal to 4 isn't doing anything, and then print x, right? X equal to 4 is not doing anything. We can remove that, right? Like, it has no meaning for x equals 4 to be there, so we remove that, okay? Now we have x equals 1. X equals 1, fine and dandy. But x equals 1 is not used anywhere else besides the print. So we can just say, yes, we know what x is. It's not like x can be anything. It's not like we can say, yes, x is gladiator, x is tomato. No. We can say, okay, x is equal to 1. We can replace this with print 1, and then remove the x, and that is our optimized code, right? So that's how optimization works. Now we have optimization, we have print 1. The final step is called code generation. I'll call it code gen. And that turns it into an exe. Code generation is basically we turn our code into an exe. Yeah. All right.